All right, let's jump straight into it. We are looking at a paper with a pretty bold title. Attention is not what you need. Grassmann flows as an attention-free alternative for sequence modeling.
I mean, that's a direct shot at the heart of transformers, right?
Absolutely. The core claim is that you do not actually need the prohibitive quadratic complexity of self-attention to build high-performing sequence models.
And the paper does this great job of reframing self-attention. It's not some magic sauce, what they call a tensor lifting mechanism.
That's your lifting.
Yeah, it basically explodes your hidden states, your simple vectors, into this massive high-dimensional space of every single possible pairwise interaction.
The famous Lalo times LD matrix. And it's this lifting that they argue is, well, analytically opaque and a huge source of the model's uninterpretability.
Exactly. It's a black box.
So the alternative they propose is completely tension-free. It's built around something called Grassmann flows.
Which is, a very geometric way of looking at the problem.
Oh, yeah.
Instead of that big matrix, they encode pairs of tokens as 2D subspaces on a mathematical object called a Grassmann manifold.
And they use something called Plücker coordinates to give that geometric object a concrete representation the model can actually work with.
And the bottom line, the performance is surprisingly competitive. We're talking perplexity scores within 10 to 15% of a similar-sized transformer, but, and this is the real kicker, the mixing mechanism scales linearly.
It's dollar or dollars, not all or dollars.
A little more quadratic bottleneck.
Okay, so let's dig into that, starting with their critique of the status quo. We all know the standard multi-head self-attention drill. You get your queries, keys, values, compute, the QTT matrix.
Right, and it's incredibly expressive, it's parallelizable, it works.
But the paper asks a really fundamental question. Is it indispensable?
And their geometric critique says, well, no. It's just one very expensive way to model the structure between tokens, this idea of tensor lifting.
Mm-hmm.
It takes your token vectors and just blasts them into that huge space of all possible pairs.
So what's so wrong with that approach? I mean, it's been the foundation of LLMs for years.
Well, the paper points to three big issues. First, it's excessively fine-grained.
Right.
Every single pair of tokens gets its own unique weight.
The state space becomes enormous.
Exactly. Second, it's massively high-dimensional, and it grows quadratically with your sequence length. But the third point is the most important, I think. It lacks structure.
What do you mean by that?
It's just hard to compress. You have this giant evolving cloud of numbers in your attention matrix, and there's no small explicit set of mathematical rules or invariants that can tell you what the whole thing is doing at a global level.
So if you're an engineer trying to debug a model or explain its reasoning, the uninterpretability isn't just because the model's big.
No.
It's because the core operation itself, that tensor lifting, resists any kind of concise description. We're kind of flying blind, just optimizing this giant matrix.
Precisely. If we want models that are mathematically traceable, models we can actually analyze, the core operations have to live in a space that is structured and finite dimensional, not one that just gets quadratically bigger and messier.
Which is the perfect segue to their alternative. The paper really shifts the whole perspective. Reasoning isn't about arbitrary correlation scores. It's about the structured geometric evolution of representations on a manifold.
And that's where the Grassmann manifold comes in.
Yeah.
If you define the Dresik-Kark ER AHA, that's just the set of all 10-dimensional subspaces inside a bigger vector space, $3.
And since they're modeling token pairs, they just set 2 to I.
Right. So they're operating in the space of 2D planes or subspaces inside a fixed low-dimensional space like any $2.
Let's try to anchor this for the listener. If a transformer uses an attention score to say how much token A relates to token B, what's the Grassmann flow doing instead?
That's a great question. Think of the $1 times LR attention matrix as letting two tokens interact in a completely unrestricted sandbox. Anything is possible. The Grassmann approach says, no, your interaction is constrained.
Constrained how?
It has to pass through a specific geometric shape, like a 2D sheet of paper, whose orientation is defined by the two token vectors themselves. The information flow is forced through this structured object, not just an arbitrary number in a matrix.
And they capture that geometry numerically with the Plücker embedding. This is what turns that abstract 2D plane into a vector that a neural net can actually process.
That's right. The Plücker coordinates, given an algebraic backbone, if you have two vectors, say $2 in your space, the coordinates are just all the pairwise determinants.
Pi vi, and the resulting vector lives in binom Q.
Exactly.
Okay, wait, so if $32, which they used in their experiments, that vector has 32 choose 2. That's 496 dimensions.
It is. It's 496. So it's a high-dimensional vector, But the crucial part is that it's fixed, doesn't grow with L, and it's not just any 496 numbers. It's mathematically guaranteed to represent a unique 2D plane because of those algebraic constraints.
So the network isn't just learning A is 0.8 similar to B. It's learning to operate on a geometric feature that is governed by known algebraic laws. We've moved from optimizing a messy tensor to analyzing flows on a constrained manifold.
Which is a much, much more promising direction for actually understanding these models.
Okay, so let's walk through the architecture itself, the causal Grassmann mixing layer. It keeps the standard transformer backbone, the embeddings, layer norm, FFNs, but the attention block is gone.
Right, and the first step is really important, dimensionality reduction. They take the token's hidden state, HT dollars, which might be in, say, $2050, and they project it way down to a small vector, zoot dollars.
And in the experiments, $3 was just 32.
Just 32.
Why is that reduction so critical? Is it just to save on computation?
It's two things. Yes, it saves costs because the Plücker vector gets big fast as $3 increases. But more conceptually, it forces the model to encode the most essential information into a compact space where the geometry is meaningful. You're forcing it to focus.
Confine the complexity. Okay, step 2 is multi-scale local pairing.
Yeah, this is clever. They just define a fixed set of small causal window sizes, something like 2, 4, 8, 12, $16. And for any given token city, they pair it with its neighbors at those offsets, 0 plus delta squares.
So you get a bunch of local geometric snapshots, and then step 3, the core of it all. For each of those pairs, they compute the Plücker vector,
which is that 496-dimensional vector we talked about, representing the 2D plane for that specific local pair.
Okay, so now we have a set of these geometric features. Step 4 is aggregation.
You've got it. They project each of those Plücker vectors back up to the model's original dimension, 2D dollars, using a learned linear map, and then they just aggregate them. Usually just sum them up.
So you get one single fused geometric feature, dA dollars, that summarizes the entire local neighborhood.
The information is flowed into the geometric space, interacted in a structured way, and now it flows back out.
And the final step is gated fusion.
Yeah, a simple learned gate, alpha, just decides how much of the original token vector to keep versus how much of this new geometric feature to mix in. It lets the model decide, at each position and layer, whether the local geometry is actually helpful.
It's a really elegant block, and when you stack these, you get the full model. But the big question is always scaling. Let's really hammer home the complexity difference.
This is the headline feature. Standard self-attention has that OLO2 LO head term. That $1,202 is what kills you on long sequences. It's the cost of computing that massive interaction matrix. But the causal Grassmann model, its parameters, like $20 and the number of windows, are fixed. They don't depend on Eulers. So the most expensive parts are just the standard FFN and linear projections.
Which are both linear and sequence length.
Exactly. So the whole thing scales as the $2. The quadratic dependency is just gone. It's true asymptotic dollar scaling.
That's a massive claim. But there's got to be a trade-off, right? By only looking at these fixed local windows, you lose the transformer's ability to just instantly connect any two tokens, no matter how far apart.
That is the critical tension, yes. And the paper argues that long-range dependencies are handled implicitly, through depth. As you stack more and more of these layers, the local geometric information gets mixed and propagated forward.
A bit like how a CNN builds up a larger receptive field.
It's a very similar idea, but in a structure that's still highly parallelizable. And the experiments seem to back this up, suggesting this repeated local mixing does a good job of approximating those richer global interactions.
Speaking of experiments, let's get practical, because the paper is very honest about its current implementation. The math is beautiful, but the code isn't there yet.
Absolutely. This is the classic academic trade-off. Their Python code is actually slower than today's highly optimized GPU attention kernels for moderate sequence lengths.
Which makes sense. You're competing against years of custom CUDA engineering for matrix multiplication. The Plücker computations just aren't optimized at that level yet.
Right. So that Eulers speedup is a theoretical proof of concept for now. It needs dedicated engineering to be realized in practice.
But the performance numbers are still really solid. What did the Wikitext-2 language modeling results look like?
So on language modeling, they tested a 6-layer and a 12-layer model. For the 12-layer one, the Grassmann LM got a perplexity of 261.1, while a size-matched transformer baseline got 235.2.
Okay, so it's in the same ballpark. That 10-15% gap shows it's a viable approach. It works.
And interestingly, the performance gap actually got a little smaller when they went from 6 to 12 layers, which supports that idea that depth helps it capture more complex patterns.
And if that proves it can model language, the SNLI results for natural language inference seem to prove it can handle downstream reasoning.
I thought this was the most compelling validation conceptually. They took a fixed Distilbert model and just swapped out the final classification head. One used a standard transformer head, the other used their Grassmann Plücker head.
So it's a direct test of the geometric mechanism on a hard inference task. And the result?
The Grassmann head actually slightly outperformed the transformer head. The accuracy was 0.8538 versus 0.8511.
That's a tiny margin, but it's conceptually huge.
It is. It's strong evidence that forcing this explicit geometric structure on the model isn't just an efficient approximation. It might actually be a better way to structure information flow for certain reasoning tasks.
So, to synthesize all this, the core takeaway is pretty powerful. You can get a strong sequence modeling without explicit attention weights as long as your model has a geometrically rich enough local evolution rule.
It really makes you question what the fundamental component of the transformer's success is. Maybe it's not the Lyell times L dollar matrix itself, but just the general principle of a dynamic token mixing evolution.
And this really opens up a path to interpretability, instead of trying to make sense of opaque attention heat maps.
Researchers can now analyze the evolution of these structured geometric objects, the Plücker vectors.
Because they're fixed dimensional, they're subject to explicit algebraic rules, and you can trace how they change from layer to layer. You could start to compute global invariance, like the overall curvature of the information flow through the model.
It means we could finally start applying rigorous tools from differential geometry to analyze these models instead of just relying on empirical performance curves. That would be a massive leap for the field.
And the paper even points to the next steps, admitting that this version only uses local windows.
Right. They suggest the future is in hybrid approaches. For example, computing some sequence-level statistics, like a mean Grassmann direction that summarizes the geometry of the whole sequence.
And then feeding that global information back down to guide the local mixing at each layer, a sort of global-to-local feedback loop.
Exactly. And of course, combining these flows with other efficient models, like state space models. Imagine an SSM handling the long-range global context and a Grassmann flow handling the structured local interactions. That could be incredibly powerful.
This has been a fascinating deep dive. It shows a concrete path for designing models whose core operations live on a structured, finite-dimensional manifold. It gives us that asymptotic dollar scaling without a huge performance hit.
It absolutely opens up a new design space beyond the transformer. It proves there's lice after two tellers.
So here's a final thought for you to mull over. If reasoning is fundamentally about controlling geometric flows on a semantic manifold, will the next generation of architectures focus less on brute force approximation like that WOL times LOL attention matrix, and more on explicitly structured geometry-aware constraints to achieve both competitive performance and true mathematical interpretability? The future of AI might be found in algebra, not just linear algebra.